All right, so here we are in section 2.7, and this is one of my favorite sections in all of calculus. You're all in for a treat because this is talking about optimization. Now, if you might be thinking, well, optimization, that's the concept of finding max and min. Well, yes, you would be right. And I like it just because it's easy for us as business majors or applied majors to kind of project where this might actually be useful in our careers. So if up to this point calculus has seemed a bit of like, why do I need this? Now you can start to maybe hopefully get a little appreciation. So just to get us warmed up, think about drawing a quick sketch of this function. Now when I say sketch, I mean literally sketch, like zero accuracy. Just get the general shape and general idea. So go ahead and think about that, do that. Okay, so now that you've done that, hopefully pause the video if you thought about it. This is, it has degree 2 because it has an exponent of 2. So therefore, degree 2, which means it's a parabola. Positive leading coefficient, which is 1. So therefore, it's a parabola opening up. Now, I really don't care where it crosses x-axis or whatever, just for a sketch, just to give us an idea, because what we're talking about in this section is max and min. So, does this graph have any global or absolute? Your book will use both terminology interchangeably, so make sure you understand what that means. So does this have any global or absolute maxes or mins? Well, what we mean by global is, if you think about it, like in the world, if I say you are globally the best baseball player, well, that means no matter where you go, there's nobody better than you. Well, so what we're going to talk about here is, does this graph have a max or a min? Well, we can see by looking at our graph, it's got a min kind of right there, right? And it would be right at the bottom. And is this a global minimum? Well, yes, it is, because no matter where you go on this graph, it's always going up. So therefore, there's never anything lower than this. So this would be a global min, or aka absolute min. So yes, it does one. It does have a global min. Now, does it have a global max? Well, no, because this graph has arrows, because it points up forever, there is no max. So every graph is not guaranteed to have a max or a min, so we have to check each one. And by the end of this, you should hopefully know how to do that. Okay, so does this graph have any blah, blah, blah? Yes, it has one global min. Okay, great. Does this graph have any local or relative minimum values? And well, the concept of local or relative means it could be something like this. So for example, if I had a graph to look like this, you see we have one maximum right there, and we have one minimum right there, but they are not global, because at some point for the red maximum, this graph does go higher. It's higher on over here. So therefore, this is a max, but it is not a global max. So thinking of it again, like the baseball player, this person is a very good baseball player, and in their neighborhood, in this area, they are the best, but elsewhere they are not. So that's why we call this a local or relative minimum, or local or relative maximum. So we have a local max and a local min. So for the graph we're looking at, though, for this graph, there are no, well, there are no local, except if you're a global min, well, then you'd also be a local min, right? If you are globally the best baseball player on Earth, then that also means you're locally the best baseball player on Earth. So what we would say is, yes, it does have one local min as well. So if a problem is asking for global or local, you have to understand that they can be clumping a global in as a local as well. So just look out for that. Okay, what do we know about the derivative of any maximum or minimum when we talk about the derivative at that point? So okay, so it's time to refresh, time to think. Okay, what does a derivative look like on a graph? Well, okay, I hope you thought about it. A derivative is the slope of a tangent line, right? So if we're at a minimum, go ahead and draw that tangent line and see what that would look like. Well, hopefully you said, all right, it looks like a horizontal line, doesn't it? Whoops, I need my graph back. A minimum, the tangent line is a horizontal line. And if we happen to have a local max or a local min, again, it's a horizontal line. So therefore, the slope is equal to 0, because if you think of it again as rise over run, we're rising 0, running 1, it has a slope of 0. So what we can do is forget all these rules we've ever learned about finding mins and maxes and using your calculator to find mins and maxes. We're done with that. We can now use calculus, because what we know is the derivative of any max or min means the slope, or the dy dx, the derivative, should be equal to 0. So for the graph up above of, let's see, let me get that down here, f of x equals x squared minus 5x plus 2, how can we use this? How can we use calculus to find the minimum value? Well, okay, so, you could use your x equals negative b over 2a and use your old algebra skills, or much better now, we know the derivative. We know how to use derivatives. So let's go ahead and find that derivative. The derivative of this would be what? 2x minus 5. So now what do we know? Any max or min, we know the derivative should be equal to 0. We know the slope should be equal to 0. So therefore, when we solve this, what do we get? Let's say add the 5 over, so that gives us 2x, and then we divide, so it gives us x equals 5 halves, or 2.5. So now we're working on finding our minimum value. We're close. So now, any minimum though, go back and think about what you're talking about. If I ask you to find the minimum, when I ask you to put your pencil on the minimum, that's a point. And to describe any point, we need an x and a y. It's an ordered pair. Right now, we have just the x. So we know it should be 2.5 or 5 halves. But what do we fill in for y? How do we get that? Do we take 2.5 and substitute it into the derivative, or do we substitute it into the original equation? Stop and think. We want y values. We want y's. Does derivative give us y's? No, that gives us slopes. Does the original equation give us y's? Yes, it does. So we're going to go ahead and substitute in 2.5 into our original equation. So we're going to do f of 2.5, which would give us 2.5 squared, or 5 halves, whatever you prefer, minus 5. I actually prefer, well, it doesn't matter, 2.5 plus 2. And this will spit out an answer for us of negative 4.25. So now we can go ahead and verify that using our graphing calculator. So what I'm going to do is go ahead and type in here x squared minus 5x plus 2. And when we hit graph, whoops, let's put our window to standard zoom 6. There we go. So negative 10 to 10, negative 10 to 10, and voila. And what we found is it looks like our minimum should be at 2.5, negative 4.25. So I'm going to do that, verify by using the calculate button. Second, calculate. Now here we can choose minimum, go option 3. And now the calculator wants a left bound. It wants to know something on the left-hand side of the minimum. So I'm going to go ahead and just hit enter. Then it wants to know something on the right-hand side. So I move the cursor over, hit enter. And then I guess, so I can move the cursor right back to where I think that minimum is, just close to it. Hit enter. And voila. So what we're seeing here is a little bit of rounding error from the calculator, because when you learn how the calculator does this, it's actually quite stupid. So nonetheless, you can see this is 2.5 and negative 4.25, so it looks like we got it right. So the power. We can now find a min or a max of anything just by taking the derivative and setting equal to 0. Now, what if we didn't know this was a minimum? What if we couldn't picture the graph and we needed to have some calculus, have a way to figure out if it's a min or a max? Well, we're going to have two methods of doing that. But the first one I want to talk about is using the second derivative. The second derivative of your function is very telling, because if you remember from the last lesson, what we learned was the second derivative of your function, if it's greater than 0, it means it's concave up. If the second derivative is less than 0, then it means it's concave down at that point. So let's find the second derivative of this graph. Second derivative of this graph. That gives us 2. So now what this is telling us is it doesn't matter where we look on the graph. It's always the same concavity because there's no x's here. There's nothing to fill in. So it's always a concavity of 2. It's always always a second derivative of 2, which is telling us what about the concavity? Well, since it's a positive number, it means it's concave up. Well, we already knew that. It's a parabola, it's opening up, it's concave up. But how can we use that on a problem where we didn't know what the graph looks like? Well, if it's a positive number and we check the second derivative at the x value of our min or max, and we can then look at its concavity and say, well, if it's positive, then we know it's concave up. Well, therefore, we know it is a min. So how we use the second derivative is we do the second derivative of our function, find out whatever that equation may be, substitute in your value for x from your critical point, from the thing you're trying to check to see if it's a max or a min. You sub that in, and then whatever your second derivative is, that tells you if it is a min or a max by if it has positive concavity or negative. Now, another way to test this, where if the second derivative test fails you, like for example, if you don't get out a positive or negative, what if you get out a 0? Uh-oh. Or what if the second derivative is just really hard to do, and I don't want to do that? Well, we have another way of doing this. What we can do is use the first derivative test, okay? We're going to use the first derivative, and what we're going to do is make a number line. So using the first derivative, remember how we did this in the last section? What we can do is find the zeros of our first derivative. And well, the good news, we've already done that. That came from right up here. We already know that this is x equals 2.5. So therefore, on our first derivative number line, we know the only zero comes at 2.5. So if I test a number to the left, if I substitute in, I don't know, the value of 0, what do we get out? Well, we get out negative numbers, right? Then if I substitute in a positive number, I don't know, let's say 5. Well, that would make what? 10 minus 5, so that makes 5. So it's a positive number. So how can we look at this and determine, saying we know we have a 0 in between, how can I determine if this is a min or a max? Well, if we remember how to read your first derivatives, this means your graph is going down. Then we had a 0. Now our graph is going up. So if you quickly sketch that, say, okay, that means my graph was going down. I hit a 0. Then my graph started going up. Look at that. It's a min. So what we can do is test the number line test. We can use it to find all sorts of interesting, to be able to interpret all of our mins and maxes. So vice versa, if I went from positive to negative, well, that means my graph was going up. I hit a peak, and then my graph started going down. Hey, look at that. That means we have a max. Or, oh, look at that smiley. That looks kind of funny. Okay, anyway, and then what if you had something really crazy, something like a negative and then a negative? What does that mean? Well, it means my graph was going down. I hit a 0, and then my graph was going down. Well, is that a min or a max? None. And so you can see, you're not, just because your derivative's equal to 0 doesn't guarantee it's a min or a max. It just tells you you had a point on your graph where your tangent line was equal to 0. And it's a point you need to check. So you either use the first derivative test, and what we're checking for is a change in signs. If you go from positive to negative, you have a max. If you go from negative to positive, then you have a min. And if you don't have a sign change, then it means you don't have a min or a max. So first derivative test using the number line. Second derivative test, if the second derivative is easy to find, then you just substitute in your number for x, find what that value is, positive, concave up, negative, concave down. So what are your steps to finding mins and maxes? See if you can pause the video and think about this and fill them in, and then unpause and let's see how you did. Okay, step 1, defining a min or a max. First thing we need to do is take the first derivative, and then do what with it? Set it equal to 0 and solve. Okay, so then once you've set it equal to 0 and solve, now step 3, I can read. Step 3 would be test, let's not do that in highlighter, test for max or min using the first derivative number line, or your other option is using the second derivative test. Okay, so I hope you have that down. And these are going to become very important going forward into your other classes. You end up using this a lot. So make sure you get that down and make sure it's not something memorized, but it's kind of more common sense. Why do we take derivatives? Well, derivatives give us slope of the tangent line. How does that help me with a max or min? Well, any max or min, the slope of the tangent line is a 0. So therefore, I set it equal to 0. Then I need to figure out, is it a max or a min? If I can't draw the graph, then I need to see if it's a max or a min. I can do that in two ways, using second derivative or using first derivative number line. Okay, hope that makes sense. So now, for problem number 2, there's not much new to learn here. We've kind of covered the big idea. So this is kind of practice. So note here, a keyword that we like to use. Instead of calling them maxes or mins, one option we have is we call them critical points. That's just hidden language for finding max or min. Okay, so let's go ahead and you can try the problem and notice what we're going to do is find max or mins for this graph using first derivatives and second derivatives and the number line test. Okay, so don't use your calculator other than to check your work. You should just be doing this by hand using calculus. Okay, give it a shot. Okay, now hopefully you've tried the problem. So let's see if you followed your steps. Step 1. First derivative. Take your first derivative. That is the world's worst prime, f prime. Let's try that one more time. Okay, first derivative. What are we left with here? That would be what? 6x squared minus 7.5 times 2, so that's 15x minus 6. Okay, now when we set this equal to 0, we have to say to ourselves, you say self, how do I solve this thing? And the first thing I notice is all these numbers are divisible by 3. So I'm going to go ahead and divide everything by 3. And that gives me 0 equals 2x squared minus, let's see, 3 goes into 15 5 times, x minus 2. Now, does it factor? And we have a couple different methods of factoring, so let's give those, I'm going to give those a shot and see what I can come up with. And what I'm seeing here, I try guess and check, and I'm seeing here, if we kind of go through it, I don't get anything. There's no answers that work. I can verify this using AC method, where I take the A and the C, so that's 2 times negative 2, which makes negative 4. What times what makes negative 4? Adds together make negative 5. Well, negative 4 times a positive 1, nope, that doesn't work. Negative 2 times a negative 2, or sorry, positive 2, nope, that doesn't work. So we are out. There's no way to factor this. So let's do the horrible quadratic equation. Let's set it equal to, let's use that. So here we go. Negative b plus or minus. I'm going to go ahead and fill this in with the video paused to save a little bit of your time. Okay, so I went ahead and filled it in there. Did the quadratic formula. Negative b plus or minus square root of b squared all over. Square root of b squared minus 4a times c all over 2a. There we go. And I just added those numbers on the inside, and I said 41's prime, so I'm not doing anything there. So voila, there's our two answers. And it kind of makes sense that we have two answers because the thing we're solving is a quadratic. Perfect. So therefore, and then also the thing we originally started with is a cubic. And if you stop and think about a cubic, those are kind of the Trifoldi graphs. So they can have one max and one min. So it makes sense that we're getting two answers. One of them should be a max, one of them should be a min. Okay, so nonetheless, we've got our x values. So to find a max or a min, remember it's a point. So we need a x and a y. So there's one of our critical values. Then the other one, instead of being plus, will be minus square root of 41 over 4. Now, just keep in mind, if MathAS doesn't tell you to round, then it's probably going to be looking for exact answers. But so then you would have to take these and sub them into the original equation. And while that's not pleasant, it should be doable. But let's just so for ease of the notes, let's go ahead and get some decimal answers, and let's take those and sub them in. So I'm going to go ahead and use the calculator to help me with that, and then I will unpause the video. And just in case I haven't shown you guys this, I wanted to show you what I did is I typed my original equation into the calculator, and now, whoops, that's not where I want to be. I want to be at the table. So now, when I go to the table, I can go ahead and type in my values, and I wanted to show you what I can actually do if I'm careful. I can actually type in the exact number I want. So 5 plus the square root of 41. You just got to be careful with your parentheses. Make sure I divide the whole thing by 4. And you see, there we go. So now I got my decimal version of x and my approximated version of y. And then I'll repeat that over here. Oops, I need my parentheses for my numerator. So parentheses for the numerator, 5 minus square root of 41. Close my parentheses for the rad. Close my parentheses for the numerator. Divide the whole thing by 4. And there we go. So now what we've got here is, go ahead and replace these with 2.8508. And if you wanted to get more exact, you can actually arrow up and highlight the numbers, and you can see you could actually get a more decimal places of accuracy. But I think these will be fine for now. So let's go negative, that's negative 0.3508. And then the y values would be negative 30.72 and 2.0955. So we've got our two critical values. Now, what are they? Are they mins? Are they maxes? How do we figure this out? Well, we have two options. First derivatives, using the number line. So let's go ahead and practice that technique. Okay, make your number line, put your zeros on it. The good news, we've already found them. We have one of them at negative 0.3508. And we have another one at 2.8508. So now what we need to do with our first derivative is substitute in values on the number line that are between each of these breakups. I need a number less than negative 3.5 whatever, and then I need a number that is between the negative 0.35 and whatever and 2. Whatever. Anyway, so one trick I like to use is I like to use something really, really big. When I'm down here to the left, I'll use a negative a billion. And the reason why is when you're substituting that into your derivative, what you could think about is if it's something like this, like a polynomial, when you have x squared, when I substitute into a billion there, that is so much bigger than any of the other terms, because yes, that's 15 times a billion, but this one is 6 times a billion groups of a billion because it's squared, so it's just gigantic. So you can pretty much just ignore the other terms, and you'd say, what's going on? Well, when I substitute in a billion, it's a billion squared, which is a positive number, times a 6, which is a positive number. So therefore, when I'm going on my number line to the negatives, it's going to be a positive number. You can verify that if you want to. Just try like negative 2, and you'll see it works out to be a positive. Now, something in between negatives and positives. Hey, because 0 is a good number. So when I substitute in 0, 0 minus 6, hey, that makes a negative. So we're in negatives in there. And then last but not least, something to the right. Well, something bigger than 2.8, so that might be like a positive a billion, where before we did a negative a billion. So here, a positive a billion squared makes a positive a billion, groups of a billion, times a positive number, which is a positive number, positive. So there we go. So now we know. Now we can look at this, and we could say what each of these points are. Because we're going from positive first derivative, remember our first derivative number line test, positive numbers, which means our graph's going up. Then we hit a 0, which means we have a min or a max, or potentially we have a place where our tangent line is slope of 0. Then we go negatives, which means our graph's going down. So therefore, at this point, we know it is a max. Then, after that point, our graph was going down, and then we leveled off, and now our graph's going up. So therefore, that means we now have a min at that point. All right, so you see how to do this? Now, we could have used the second derivative test too. Let's make sure we understand how to use that. The second derivative test says take the derivative of your derivative. So the derivative of 6x squared would make 12x. The derivative of negative 15, it says just negative 15. And there we go. So now what we can do is use the second derivative and use our test values. So, or use not our test values, use our zeros. So I'm going to actually check it at negative 0.3508. When we go ahead and substitute that in, what kind of number do we get? And the nice thing is we don't really care if it's what it is. All we care about is it positive or negative, because positive means concave up, negative means concave down. And so if you think about it, negative times 12 and change is going to make a negative number. A negative number minus 15 is going to make a negative number, which means we're concave down because negative people are sad, and therefore that means we have a max. Notice that that verifies or that agrees with what we already found. So now I'm going to use my other x value of 2.8508, and I'm going to go ahead and substitute that value into my second derivative. So that's like basically 3 times, or heck, even if we call it like 2.5 times. 2.5 times 12, that's going to be bigger than 15. So, and it's a positive number, so it's something really positive. Minus 15, that's going to leave us with a positive, which therefore means we're concave up, which means we have a min. So there we go. We have now used second derivatives to test it to see if we have maxes and mins. We use the first derivative number line to test to see if we have maxes and mins. We're making great progress. Okay, I hope that helped. Now let's go ahead and look at this next problem. What's interesting about this one? Well, I don't know. Give it a try. Pause the video, see how it goes, and let's see what happens. Okay, so once again, hopefully you said, look, the problem's asking me for critical points, which therefore means I want maxes or mins, and what we know about any max or min is the derivative is equal to 0. So hopefully you went ahead and took your first derivative, set it equal to 0, and realize this is all, again, divisible by 3. So that gives us, what, x squared plus 4x plus 4. And now we're going to see if we can factor this thing. And by golly, I think this one's going to factor. Let's find out. Let's see, x plus 2 times x plus 2. What does that do for me? 2 times 2 makes positive 4. Add them together makes positive 4. That looks great. So therefore, I have a min or a max at x equals negative 2. Because remember, if you don't remember, we take each of our factors using the zero product property. And we say 0 times anything makes 0. So I just look at these individually, solve the problems. Well, since they're the same problem, I'm going to get x equals negative 2. So now, therefore, I need to test it at negative 2. Where do I plug that into? I substitute this back into the derivative. No. I don't want that because the output is slopes. I already know what that will be. I push that in, I'll get out 0. I know this. I want to put it in to get my y, so I'm going to substitute it into there. So let's go ahead and sub that in and see what value we get. Okay, so I got 1 when I substituted that in. Fantastic. So now I need to determine, is this thing a max or a min? Well, let's find out. Let's practice whichever test you want. I'm going to go ahead and use the, I don't know, second derivatives. It seems pretty easy for this one because the second derivative is relatively simple to find because it's just power rules. That gives us, what, 6x plus 12. So therefore, when I test this at negative 2, that's going to give me 6 times negative 2 plus 12, which is going to give me negative 12 plus 12, which gives me 0. Well, that's interesting. What does that mean? What does that mean? Well, we kind of learned that second derivatives at 0 can be inflection points, right? So that's kind of interesting, but I don't know if that's a max or a min. Might be an inflection point. So when the second derivative test fails, we can always go to the first derivative number line test and see what that looks like. So let's go ahead and throw this on here. So that's negative 2. Okay, so we got negative 2 on our number line. Let's substitute in some value less than negative 2, like, I don't know, billion, million, quadrillion, something really big, negative. But negative something really big squared would make a positive. Positive times 3 makes a positive, so therefore the whole thing's going to be a positive. And then something on the other side, how about, I don't know, a positive a billion. A positive billion squared is a positive. Positive times positive is positive, so therefore it's a positive. Interesting. So what are we seeing here? The graph was going up, and then we hit our 0, and then the graph started going up. Oh, okay. So therefore what I'm seeing for our graph, it kind of, to me, looks like it is an inflection point, right? It was concave down, switched to concave up, but there was no real max in between. And if you go ahead and look at the graph of this, you'll verify it's a little more shallow than how I drew it. It kind of goes more like that, but the general idea is there. So the reason I like this problem, I wanted you to see it, is it gives you a really good example of a time where one of the tests fails and you have to use the other one. All right, now here is a super duper interesting problem. Okay, find the critical points of this function. Oh my goodness, I have no idea what this looks like. None. So, but can we do the derivative? Let's find out. H prime of x is equal to, all right, so here we go, 2. This is a chain rule, right? So that comes out to the front. Leave the junk alone. Subtract 1. All right, now, so that we did that, scratch that out. Do the derivative of the inside. Derivative of natural log is 1 over x. Okay, good. Do the derivative of that times the derivative of the inside is x. That's just 1, so we don't really need to write that. Okay, so done with that part. Then plus, now the derivative of e to the x, well, that's the favorite kind of derivative because it's just e to the x. It's really e to the x times natural log of e, but natural log of e is 1, so we don't need it. So there's our derivative. So now what do we do with this? Set this thing equal to 0, and we need to solve it. And I'm going to clean this up a little bit. 2 times 1 over x is 2 over x times the natural log of x plus e to the x. Okay, all right, easy enough. So who knows how to solve this? Yeah, don't start raising your hand too quickly. All right, so why I wanted to do this problem is I wanted to show you we can use our calculator to help us. What I'm going to do is type the function and just this part, into the calculator. And some students actually prefer to, instead of solving like this, they like to take one term and subtract it over to the other side. And the reason why is what we're going to end up doing is looking for an intersection between this graph and this graph. And if you don't subtract it over, what you end up looking for is where this whole piece hits 0. It hits the x-axis, and it's just whatever you prefer. One way you're looking at x-intercepts, the other way you're looking for the two graphs intersecting. So what I'll go ahead and do is type in the first equation. So it's negative e to the x, and that's it. You're done. You move on. And then the other one is numerator of 2 times the natural log of x divided by x. So there we go. So now when I hit graph, I'm looking for, oh, there's my first graph, and there's my second graph. So to find the solution for this, we're going to go ahead and say calculate. Second, calculate is how I got here. And what we're going to do is look, oh, look, option number 5 says intersect. That says intersect. So it's asking me intersect of the first graph. Yep, that's what I want. Hit enter. Then you say intersect of the second graph. Oh, yep, that's what I want. Hit enter. And now it's time for a guess once it goes. Oh, excuse me, what's your problem? Oh, I actually have to move the cursor so it's on the graph. There we go. Now it wants a guess. I'm going to go ahead and move this close, because if it actually hit in 2 places, you're telling me which one you want. And be mindful of what you actually are seeing on the calculator. Because the way we wrote it, what we're saying here is the y value should be equal at the same place the x values are. Well, the way we wrote it here, we don't really actually have any y values. What we have are x values, though. So the x value is the only thing we actually care about. What we've just found is the x value, where these two graphs intersect, is at 0.5885485. Or what we're saying here is when I substitute in that into this equation up here, it'll equal 0. So we got that's our x value. Whoops, excuse me. So now how do I get the y value? What do? Well, I have to take this whole thing and sub it back into the derivative. No. Back into the original. So go ahead and use your calculator to get that. So there we go. That's what I got when I subbed that into my calculator, and I got my y value. So now, how do we tell if this is a min or a max? I don't really want to do a second derivative. That doesn't sound like a lot of fun, but I could. But to me, it seems like the first derivative number line test may be the way to go. So let's do that. So what I'm going to do is do the number line. Go ahead and say, I know, at 0.588 885 is my 0, so I just need to test something to the left of it. So we could plug in, say, a half into your derivative and see what that comes out to be. And then maybe on the other side we could substitute in 1, substitute a value of 1 and see what that comes out to be. So I'll go ahead and pause the calculator, or pause the video, you guys go ahead and do that. And just as a reminder, this is kind of a perfect opportunity if you wanted to, where you could go into your calculator here to get these values and type in your original equation to y1. So that would be ln of x quantity squared. Whoops, missed the squared. Squared plus e to the x. And then what we could do is have the calculator do the derivative for us, because we're going to just be substituting in values. So that's not too bad, right? Oops, excuse me. So we want to go to math, option 8, and derivative. There we go. X vars, go over y1 where I did this in the last video. There we go. So now when I go to the table, the values I want to test here was 0.5, something to the left, and maybe 1, something to the right. And what we can see for our derivatives, which is the y2 line, to the left we had negatives, to the right we had positives. So now that tells us our graph was going down, then going up. So therefore, this value is a minimum. All right, so next, how is this problem different than all the other ones? And finally, this will be the last problem of this homework set, or this lesson. Notice this problem is the same, except they're limiting our domain. They're saying find all the critical values, mins and maxes, for this graph over that domain. And this actually drastically changes the process. Well, actually, the process is very similar. I'm still going to use calculus. I'm still going to use first derivatives. So you go ahead and do that and find the first derivatives for your function, do everything like normal. Then I'll pause the video and I'll tell you how to deal with this. All right, so hopefully you've done this part already. You said, all right, my derivative is 2x minus 5, so therefore that's equal to 0. And oh, yep, that's kind of nice. That's 5 halves, perfect. So then I can go ahead and substitute that back in and get my actual value. Let me get that. And this time it's the same values as before, but this time I just did it with fractions. So I have 5 halves and negative 17 fourths. Fantastic. So therefore, and if we stop and think about this, we already knew it's a graph parabola opening up. That was our value. But now notice we're not going from negative infinity to infinity. We're going from 0 to 10. So what that means is wherever the graph happens to be at 0 up to 10. So now we're going to have endpoints. We're going to have a start and a stop to this graph. So this adds in a whole new dimension to this. Oh, and we already knew this was a min. Okay. So now, though, what you can see here is we can actually really focus on the concept of absolute min, and where the graph before, when it was a parabola, wouldn't have had a max because it would have been going up forever and ever and ever, right? Now that we have these stopping points, excuse me, let me get back to my screen. There we go. Now that we have these stopping points where, there we go, what we actually will have is an absolute max, because over this interval, do you see there is a place where we go no higher? There's a place where you never go any higher because we're restricted from 0 to 10. So we're going to have an absolute max at 10, at least by the way I drew the picture. So how do we do this? How do we check this to figure this out? Well, it's actually really, really simple. We are going to create a list of every test point that we need to test, every value we need to test. Well, our first set of values came from our first derivatives, okay? So what you're going to do is do work like normal. There we go. You're going to do your work like normal, make a list of all of your first derivatives. Then you're going to make a list of your endpoints, the points that come from the domain restriction. So I'm going to substitute in 0, I'm going to substitute in 10. So when I substitute in 0, I get out 2. When I substitute in 10, let's see what that is, 100 minus 50, so that's 50, 52. And the rule here is we're only going to worry about endpoints if they are absolute. If it's a relative, we ignore it. We're not going to say this is a relative min or relative max, because how do I know? It could be either. Because if the graph, I don't know, it's like an absolute, it's a relative middle. So yeah, so the endpoints, we only worry about them if they're absolute maxes or mins. If you're going to your boss and they're saying, what's the best we can do? Well, you're not going to tell them this is the best, the minimum. No, and so you're going to tell them, well, at 10, whatever 10 is, 10 cars, 10 years, 10 turtles, whatever it may be, that is your absolute best. That's your max. And how can you see that from these points without having to draw graphs? Well, just look for the one with the biggest y. If it has the biggest y, that one is your absolute max. Now, anyone that has the smallest y, well, then absolute min. And if it's something in the middle and it came from a derivative, well, then it would be a local min or max, and you'd have to use your second derivative to test that, or your number line test to test that. But if it didn't come from a derivative, it came from the endpoint like this one, then it is a big fat nothing. We don't care about it. So there's your answers for this problem. We have one right here. At 5, 2, negative 17 fourths. 5 halves, negative 17 fourths, we have an absolute min. And then at 10, 52, we have an absolute max, and that is all she wrote. So the big idea for this section, what's the big idea for this section? Make your notes, make your summary. Big idea. All right, well, it was about maximization. It was all about optimization, finding mins, finding maxes, maximizing profits, minimizing costs, whatever your line of business may be. So how do you do that? Well, to find absolutes, we're always looking for, or to find mins and maxes using calculus, we're always looking for derivatives that are equal to 0. Did not mean to do that. Excuse me. Let's try that one more time. There we are. Okay, finding zeros. Mins and maxes mean your slope, your derivative, is equal to 0. So you take your first derivative, you set equal to 0, and you solve, right? Then, if you have endpoints to your system, to your function that you're trying to find the critical points of, then you just need to make a list of all the endpoints, find their y values, and if it happens to be the biggest y value, it's an absolute max. If it happens to be the smallest y value, it's an absolute min. If it's something in between, it's nothing. Okay, so that's the big idea. It's fun. It uses derivatives. It's not always easy. And it is absolutely okay to use your calculator to help you solve something that looks like this. That would be extremely difficult to solve. Yes, I expect you to be able to solve quadratics by hand. But something like this, yeah, don't waste your time. Just go straight to your calculator, help you solve it. And on a test or something, you could absolutely write, you used calculator to solve, but then you're still showing me all your work, how you got your x and your y's, and you're showing me your first derivative number line test. So you get the idea, where you're still showing me work, and you kind of use the calculator to help you out with that little part. Okay, best of luck.